Okay, this is going to be our first video in our first module of this course. So this would be the first module that we're going to be doing in Physics 112, and this video is intended to map to sections 21.1 and 21.2 of the text. We're going to be talking about electric charge and electric fields here. So generally speaking, I'm going to try to stick very, very closely to the text, and I'm going to try and have maybe each video cover one or two sections of the text. In this case, we're going to be covering two sections of the text in one video here. They kind of go together well. They cover a lot of sort of qualitative ideas on electric charge and electric field, so there's not going to be a lot of calculation in this video, but we're going to talk about a lot of concepts that are going to be sort of useful, and we're going to come back later on and really do the calculations involved in figuring out how some of these practical situations work in subsequent sections. Okay, and so let's start off here. Before we get into the actual content of chapter 21, sorry, we are going to, well, I'm going to take a step back here, and we're just going to take a look at fundamental forces in general. If you did your Physics 111, or whatever your first year mechanics course was on using this textbook, you would have seen in chapter 5.5 or in section 5.5 that they discuss fundamental forces. Most textbooks will have a section like this in your first year mechanics course. And so whatever textbook you used, you could always look back to that section. But I'm just going to sort of pull out some quick points from that section in this textbook, just to introduce the ideas of electromagnetic interactions. Okay. So looking back, you guys would have spent a significant amount of time in Physics 111 studying the effects of the gravitational force. And gravity is one of the four fundamental forces, right? And we might have sort of, as I said, talked about this in 111. So there are four fundamental forces. We have the gravitational force, we have the electromagnetic force, and we also have the so-called strong and weak interactions, which I'll briefly mention after we discuss gravity and electromagnetism here. So as I said, in Physics 111, you would have spent a significant amount of time sort of studying the effects of the gravitational force. The gravitational force is what gives objects their weight. It's what keeps the planets in orbit, and it does a whole bunch of other things that we would have looked at in Physics 111. Okay, and so that was the focus, or one of the focuses of Physics 111. Here in Physics 112, we're going to be looking at a different one of these fundamental forces. We're going to be looking at electromagnetic interactions. Electromagnetic interactions, we're going to find, sort of relate electricity and magnetism. We're going to find that electricity and magnetism are forces that are closely related, and we're going to get to that sort of at the end of the course. That's sort of one of the punchlines toward the end of the course. But we're going to treat them both sort of separately for now, electric forces and magnetic forces, and we're going to talk about those at some length in the coming weeks here. So atoms contain positively and negatively charged particles, and so these atoms can exert electric forces, and we're going to take a look at that here in a moment. Okay, we've sort of been exposed to electromagnetic interactions in the past without maybe noticing it so much. Contact forces that we studied in Physics 111, such as the normal force, or the force of friction, rely on electromagnetic interactions, and we're going to see kind of how that's the case as we go on in this course as well. We're going to spend basically all of the stuff that we talk about in this course is going to be related to the electromagnetic interaction. So we're not really going to talk much about gravity. I may throw in a couple of problems to compare gravity to the electromagnetic interaction, but in general, all of our work is going to be focused on electromagnetism. Okay. So when we're talking about the electromagnetic force on molecular scales, we're going to see that really we're not sort of throwing out gravity just because we don't want to deal with the complexity of the problem. We're really going to see that gravity has an almost, well, has a truly negligible effect at these scales. So if we look at, for example, and I haven't left myself much space to draw here, but I'll kind of draw something out. So I'm kind of looking at this bullet point here, and if we look at, say we put two protons close together, and we're going to talk about what protons are for people who aren't sort of familiar with that in a moment. But if we put two protons together, these are going to be two positively charged particles. If we put two protons side by side, some distance apart, and we took a look at the forces at play here, we would find that yes, there would be some small gravitational attraction between these two protons. So they would be drawn to each other through the gravitational interaction, right? But there would also be a repulsive force from the electromagnetic interaction. So we would have some force from the electromagnetic interaction forcing these two apart, right? And if we were to compare the magnitude of these forces, if we were to compare the magnitude of the gravitational attraction to the magnitude of the electromagnetic repulsion, we would find that the electromagnetic repulsion would be roughly 10 to the 35 times greater than the gravitational attraction. So that's a 1 with 35 zeros after it. So we can really see that on these small scales, the electromagnetic forces really dominate, and there really is no sense in looking at any sort of gravitational contribution to what's going on here, right? Okay, so that's sort of the sort of brief introduction into what we're going to be looking at. So electromagnetic interactions, and why we're really going to be focused primarily on electromagnetic interactions. Now if we're talking about much larger objects, let's say we're talking about planets or something like that, in general, these objects tend to be neutrally charged, right? At least they have a net neutral charge, and so there's no net charge on say let's say we're looking at the forces at play when we're looking at the Earth and the Moon. Well, there isn't going to be a very strong electromagnetic repulsion or a very strong electromagnetic attraction, because the Moon and the Earth are both electrically neutral. So gravity in this case takes over and really dominates, right? And this is why sort of on macroscopic scales we look at gravity more sort of intensely, and on these smaller scales where we can more easily have objects that carry significant amounts of charge compared to their mass, this is where really electromagnetic interactions sort of take over, okay? And so I mentioned that there were four fundamental forces. We briefly discussed gravity, which you guys are already quite familiar with. We talked a little bit about the electromagnetic interaction. These two interactions, gravity and the electromagnetic interaction, are the two sort of forces that we see on macroscopic scales. The remaining two forces, the strong and weak forces or interactions, are not things that we experience in the sort of macroscopic world. These forces only really play sort of dominant roles at subatomic levels, and so they're not something that we're A, sort of familiar with in the macroscopic world, and B, they're not things that we're going to be talking about in this course. You'd have to go on to further courses in physics to delve into these topics. So I'm not really going to talk about these, aside from the fact to say that these are the two other fundamental forces. They're only experienced at very, very small distance scales, and we're not really going to talk about them in this course. I guess I'll also mention, I have a little note here, that the strong interaction is where I spend a lot of my research time. So if you guys are interested, feel free to ask me, at any point. But really, it's not something that we're going to be involved in looking at in this course, and so we can move on from there. I'm just going to clean up the slide a little bit, because this slide is going to become the course notes that I'm going to post. And yeah, so you guys will see that as I continue in the course, I'm going to sort of post these notes. I'll have one set of notes per video that I post. They're going to have some additional writings that I'll put on them as we go, but I'm only going to leave sort of the important things that I want you guys to have for the notes on there, and try not to make too much of a mess of the slide here so you guys can read them in the future. Okay, so we took a look back at a previous chapter just to get the idea of these four fundamental forces. Now let's focus in on what's going to become the focal point of the course here, electricity and magnetism. For this first chapter, chapter 21 in the text, we're going to be looking at electric charge and electric fields. So we start off by just looking at static electric charge in this course. And later on, we're going to include ideas like moving electric charge. We're going to see that this introduces a whole host of other interesting things that we can do with electric charges. This is going to lead us into an understanding of magnetism. And eventually, if we have time in the course, and I'm going to try to make sure that we do, this is going to lead us to an understanding of the nature of light, which is also quite interesting. Okay, so we're going to try to get to all of that. We're going to find that while many of these ideas are conceptually simple, they kind of get difficult when we try to apply them to practical problems. So in this first video, in these first two sections, we're going to talk about a lot of the ideas that are going to be sort of covered in the first third of the course, really. We're going to talk about them all here in this one video, and then we're going to spend the next few weeks developing the math and the understanding that we need to be able to actually calculate some of these quantities in practical physical problems, right? And the reason for this is that the math that we need, the tools, the mathematical tools that we need to tackle some of these problems are a little more complicated than for example, the ones we needed in Physics 111, and a little more complicated than a lot of people at this stage are sort of equipped to easily deal with, right? We're going to need to use some ideas in geometry and some ideas in integral calculus that people might not be familiar with yet. So Physics 112 has a co-requisite of Math 112, and this is because in Math 112 you guys are going to be covering a lot of integral calculus, and we need a lot of that integral calculus in Physics 112. Unfortunately, you may not get to the integrals that we need in your math course by the time we need them in the physics course. But that's fine. I'm going to take some time to go over the specific math that we need for each of these problems that we're going to be tackling. I'll give you guys some techniques that you can use to solve these problems, and we'll sort of move forward from there. Okay. Okay. So now delving into the real sort of specific sections of chapter 21, we're going to start off looking at electric charge, and this sort of maps to section 21.1 in the text. The text will often go into a little more detail. Generally speaking, most of what's in the text is included in the course. So what I do is I take what's in the text, I kind of boil it down into point form and the key points, the key takeaway messages that you guys should keep in mind as we move forward in the course. And so this way you have the text that you can read, which has sort of full detail and more explanation. You have this video, and you have the notes, which are kind of a boiled down point form sort of review of everything. So hopefully this way we're coming at it from a number of different angles, depending on how you like to look at it and how you like to review. You can make use of any of these different resources to sort of make sure you have the ideas firmly in your head, right? Okay, so in section 21.1 here, what I've done is I've broken this down into point form. These are sort of point form ideas we should keep in mind when we're thinking about electric charge. Okay, so the first thing to keep in mind is that electric charge is a fundamental attribute of any particle. It's just like mass in a sense, right? Every particle has some mass. Every particle will have charge. Either it'll be positively charged, negatively charged, or it'll have a net neutral charge, right? And so this is something we want to keep in mind. This is just a fundamental attribute of any particle that we're dealing with, okay? Electric charge is quantized. So what do I mean by quantized? Electric charge comes in discrete packets. There are sort of minimum sized chunks of electric charge that we have to be moving around, and below that we're unable to move charge. And we're going to sort of talk about that in a further bullet point down here when we get to it. But for now, just keep in mind the idea that oh, did I close this? Oh, that's unfortunate. Let me reopen this and get right back into it. Where was I? Here we go. Oh, no, that's the wrong program. One sec. In fact, I'll just pause the video for a moment while I reopen this. Okay, so back to what I was saying. Sorry about that. So we were here, right? And we were talking about electric charge being quantized. So it comes in discrete packets, and we'll talk about what those discrete packets are in a moment here. Electric charge also obeys a conservation principle, and this is going to be one of the topics that we're going to discuss a little bit later also. But basically, electric charge is never created or destroyed. It's just moved around, right? So we're going to see that electric charge in a closed system is conserved. Okay. When charges are at rest in our reference frame, they exert electrostatic forces on each other, right? And so this is what we're going to spend next video talking about. This is Coulomb's law, and we're going to spend some time talking about how to calculate these forces, how these forces are going to work. And as I said, this is Coulomb's law, and it's going to be the subject of our next video. So just keep in mind that when at rest, these electric charges will exert electrostatic forces. Okay. Electric charge comes in one of two flavors. It can either be positive or negative, and that seems sort of obvious to say. Most of us, for our whole lives, we've seen batteries, we've seen things with a positive and negative charge. We've done other courses in physics where we talk about this, right? But it doesn't always have to be that way for every force, right? In the case of gravity, there's simply mass. Gravity, as far as we know, is always attractive. Things either have mass or are massless, so they only have a magnitude of one sort of quantity that can only be sort of positive in a sense, right? But here we have negative and positive, and other forces, could have other charges. But in the case of electromagnetism, we only have the choice of a positive or negative force. Okay, we're going to see that like charges repel and opposite charges attract. So two negative charges will repel each other. Two positive charges will repel each other. A negative and a positive, or a positive and a negative, will attract. Okay, and we're going to take sort of more of a look at that as we go on here also. The SI units for charge are coulombs. For now, we're just gonna state that they're coulombs. They're called coulombs. They have the symbol of capital C. Later on, we're going to sort of define these in terms of magnetic forces and amps. But for now, just take for granted that we call the SI unit for charge a coulomb, and we'll define it sort of in terms of more fundamental units later on. Okay. And operationally, when we're sort of doing these calculations, we're going to see that the smallest sort of unit of this charge, sometimes called the natural unit of our charge, is this E that we have down here. This is the charge on a single proton. And so the charge on a single proton is 1.602 times 10 to the minus 19 coulombs. And this is the sort of smallest unit of charge that we are free to work with, right? Like I mentioned above here, electric charge is quantized, so we can't really change the charge on an object by, say, half of an E. We have to change it always by integer values of E, right? And we're going to kind of work with this a bunch as we go on. This is definitely a number you want to commit to memory because you want to know what the charge on a proton, and this is also the charge on an electron, except in the case of an electron, it picks up a minus sign, right? So as far as we know, to within experimental uncertainty, the charge on an electron and the charge on a proton have the same magnitude, right? They just have opposite signs, okay? And as far as we know, to experimental uncertainty, this is true, okay? So those are sort of the key points that we want to keep in mind when we're talking about electric charge. We're going to break down each of these points much more in detail as we go on, but these are just the key things we want to keep in the back of our minds when we're thinking about electric charge in general. Okay. So let's now take a moment to take a look at how charged objects are going to behave by looking at figure 21.1 from the text, which I've copied over here. Okay, and again, I'm going to try to use as many of the figures from the text as possible that fit in nicely into lectures, so that you guys can always go back to the text, and if you want a little more, it's kind of right there for you. Okay, so let's take a look at what's going on in this image. In part A here, we start off with two plain plastic rods. One of them is sort of hung from this apparatus we have here. It's free to swing, and we have the other one in our hand. We bring them close together, and since they are both neutral, they both have no net electric charge. They basically do nothing, right? We bring them together. They don't attract. They don't repel. Nothing happens. Let's say then we were to take both of these rods and rub them up against a piece of fur here. Okay, so we rub them up against a piece of fur. They both then pick up a net negative electric charge. If we then mounted one of the rods back on our apparatus so that it could swing freely, and we tried to approach the other rod to it, we would find that there's a repulsive force. As we bring the rod in our hand close to the one hanging, they repel each other, and it pushes the rod that's hanging from the swing here away from us. Okay. If we repeated this same procedure with plain glass rods, and we rub them with silk, we would see that we have the same thing happening, except in this case, both of the rods would pick up a positive charge, and so because they're both now charged and they have like charges, they repel, right? So again, we have the same situation here where we have this repulsive force, right? If we then took one of each of these rods and hung them on a setup sort of like we see here, where we have two swings that are free to move in this direction, we will see that there is a net attractive force, right? The negative and the positive will result in a net attractive force, and these two rods will tend to move closer together. We can also see that if we then brought the silk that we were rubbing against the glass rod up against the glass rod, which is now positively charged, well, the silk itself picked up the negative charge. It pulled some of that negative charge off the glass rod, and so it has a net negative charge, and so we would see that these would be attracted to each other, and the same would be true for the plastic rod and the fur. Okay, so this is interesting. We can kind of see, we could do this experiment in the lab. We could see how this kind of works. We charge the rods by rubbing them up against things, but we don't actually see anything happening, right? The rods don't change their appearance. Nothing seems to visibly change as we rub these rods with these different materials. So what's really going on? Like why are these rods getting charged, and what's actually happening sort of under the surface here that we don't see, that's causing these things to attract and to repel each other, right? Well, so to get at this question, we need to look at atoms and sort of how they're made up, and to look at the atoms that make up these rods. We're going to take a look at this sort of schematic diagram. I think this is a figure, or I can pull it up here. I think this is figure 21.2 from the text. Maybe, no, this is 21.3 from the text. And here we have this little mock-up of what an atom would look like, right? So we're probably, most of us are probably somewhat familiar with this idea. We have an atom, we have our atom's nucleus is here, made up of protons and neutrons. It's this tiny little core of our atom, and around it we have these large clouds of electrons, which are negatively charged, right? And our protons carry a positive charge in the nucleus, right? And so one question that may sort of occur to us is we just talked about how positive charges repel each other. So how is it that all these positive charges stay tightly jumbled in the nucleus, right? And this is a question that we would need more physics to answer. We would need to start talking about the strong nuclear force, or the strong force, and the residual strong force that's left over, which kind of keeps these protons bound tightly in the nucleus. But that's a question that we're not really going to be able to address in this course. So if you're interested in that kind of stuff, I would say sort of stay tuned and look at future courses in physics to answer those type of questions. But for now, what we have is all of our sort of constituents, all the parts of our nucleus tightly bound in the nucleus. They are either neutral in the case of neutrons, electrically neutral, or positively charged in the case of protons, which we see here. indicated by these red spheres, right? And then our electrons are just whizzing around in these probability clouds, making up the sort of outer shell of our atom, right? And so, well, this is sort of a side that I mentioned here, which kind of discusses why these protons are tightly bound in the nucleus. It's nice to keep in mind that the protons and neutrons, which make up this core, this nucleus of our atom, have a radius only on the order of about 10 to the minus 15 meters, right? And let's say the electrons, which are whizzing around outside in these clouds, have a radius of roughly something like 10 to the minus 10 meters, right? So a nice way to sort of visualize this, and this is a direct quote from the textbook, is if the atom were a few kilometers across, the nucleus would only end up being the size of a tennis ball, right? And so even though the nucleus is much, much smaller than these clouds of electrons, which are whizzing around outside, right, much, much smaller in volume, it does make up roughly 99.9% of the mass of the atom, even though the remaining 0.1% of the mass takes up the vast majority of the volume, right? Thinking back to a tennis ball versus a sphere that's a few kilometers in diameter, right? And so that's sort of the idea that we want to keep in mind in the when we're thinking about an atom here. But we need to get to this point of charge, right? Like why are our rods getting charged? Well, if we have these atoms, so long as the number of protons and protons in the nucleus and the number of electrons are the same, we end up with atoms that are neutrally charged, right? And this is again an image from the textbook. This is just a few different. Well, this is a lithium atom and a couple of lithium ions. This is 21.4 from the textbook. So when we're looking at this, we can see that we have our lithium atom here. So we have an equal number of protons. We have 3 protons in the nucleus, and we have 3 electrons in our electron shells. We also have 4 neutrons that are not interacting electromagnetically. They are neutral, right? But if we then strip off one of the electrons, we end up with a positively charged lithium ion here. We end up with 3 protons and only 2 electrons, right? And this would then have a net positive charge, right? And in the case of part C here, we've gained an additional electron. This is a negative lithium ion. We have 4 electrons and 3 protons, and so we end up with this net negative charge, right? And this is really what's happening when we're rubbing the rods on these different materials. We're passing electrons back and forth between the rod and the material, depending on which type of material and what type of rod we're using, ending up with rods with some net charge, and in the end this allows us to see this sort of attractive or repulsive force depending on how we set things up, right? Okay, so that was a sort of brief primer on electric charge. I mentioned above that electric charge is conserved. We're not going to make a whole lot of use of that point right at this moment, but we do want to keep that in mind, so I've boxed it off here. Electric charge is conserved, and what does that mean? That means that the algebraic sum of all electric charge in any closed system remains constant. So if you have a closed system, no charge is ever created or destroyed. It's just moved around within the closed system, right? And so, again, when we're talking about the rubbing of those rods on the different materials, we're really only talking about passing electrons from one material to another. We're not creating or destroying any charge there, okay? And so to close off section 21.1, we can quickly discuss the sort of test your understanding question at the end of that section. I kind of like this one, so I thought I'd bring it up here. We have 2 charged objects. Okay, so imagine that we have 2 charged objects. I'm just going to draw 2 objects here. They have some charge, but we don't know what the charge is. And these 2 charged objects repel each other. So we see that as we try to bring these closer together, there's some force repelling these 2 objects, right? what does this tell us about their net charge, right? So, I mean, we can sort of think about what the four cases here are. We could either have this object with a positive charge and this object with a positive charge, or we could have this object with a positive charge and this object with a negative charge, this object with a negative charge and this object with a negative charge, or this object with a negative charge and this object with a positive charge. Now, which of these cases is possible, or is what's actually happening when we're experiencing a net repulsive force, right? Well, we know that like charges repel each other, and so we must have this situation where they're both positively charged, or this situation where they're both negatively charged, right? And that's really sort of the point that we're trying to get to here. What this net repulsive force is telling us is that we have like charged objects. These things have like net charges, so either they are positive or negative, but they have to be the same, otherwise we would be getting a net attractive force, right? Okay, so as I said, we're going to cover two different sections in this video. Oftentimes I'll only do one, but this time they kind of bundled up nicely because they're mostly just qualitative ideas, and so we can kind of discuss them both in this one video. So in section 21.2, we're talking about conductors and insulators, and we're also talking about induced charge, okay? And so let's start off with conductors and insulators. I think most of us probably already have a pretty good intuitive understanding of how conductors and insulators work. If you grab onto a wire that's plugged into the wall, the reason that it doesn't shock you is because it's covered in an outer plastic or rubber sheath, which is insulative, so the current doesn't flow into your body, right? But if you touch the end of a wire which is plugged into the wall, you touch the copper end of it, you're going to get a shock, and that's because copper conducts electricity, right? So that's just a very, very basic sort of, the basic idea that we're trying to get to here, and this is our sort of intuitive understanding from the sort of modern day, everyday things that we sort of see in the world around us, right? So what's sort of going on here, right? We know that some materials allow charge to flow freely from one region to another. We call these conductors, and other materials don't allow charge to flow freely, and we call these insulators. There are some things that sit sort of in the middle ground that are semiconductors, but by and large, most of the things that we deal with in the real world. Oh, and let me pause the video for a second here. I have to cough. Excuse me. Right, so by and large, most of the things that we deal with in the real world are going to be pretty much either purely conductors or purely insulators, and the things which are in between aren't things that we're going to be talking about very much in this course, and aren't really things that we run into too much in the real world. Like generally speaking, metals are conductors, and we see things like glass and rubber that are insulators, right? And so let's take a look at figure 21.6 here from the text, and sort of see, again, with a charged object, what we can do with these conductors, and sort of what this setup is going to end up looking like as we end up charging or discharging things, right? So I wish I would have made this a little bit larger, but we'll try to work with it as is. So what do we have in part A here? Well, we start off with a metal ball. This metal ball here starts off with no charge on it, so it's electrically neutral. And we hang it with this insulating nylon thread. We then bring this charged plastic rod, which has a net negative charge, sort of closer to the metal ball, and then we connect the two of them with a copper wire, right? So we connect the two of them with a copper wire. Copper wire is conductive, and so what do we expect to happen? Well, we would probably expect that some of the net negative charge from the plastic rod would flow into the metal ball, and that's in fact what we do see, right? So we can see that in part B here. If we then remove the copper wire, we're going to have some of that negative charge that's flowed across the wire into the metal ball staying on the metal ball. So now the metal ball has a net negative charge, and the rod still has a net negative charge. So if we try to bring these together, well, they're going to have a net repulsive force, right? They're going to be pushing away from each other, and so we end up being able to push the ball around with the rod, right? If we then replaced our negatively charged rod with a positively charged rod, say from the previous example that we looked at, well, we could then pull the ball along, right? Because there's going to be an attractive force between the net negative charge on the ball and the net positive charge on the rod, right? And this kind of works how we would expect it to, right? Let's say, for example, though, that in part A here, in image A, let's say that we didn't connect the charged plastic rod and the metal ball with a copper wire, but instead we connected them with a rubber band or some sort of insulating material, right? Well, in that case, the charge would not flow across whatever this connection was. Say this copper wire was rubber. It wouldn't flow across that connection. The metal ball would not pick up some of this negative charge and would remain uncharged, right? It would remain electrically neutral. And that kind of leaves us with a question, well, would the charged plastic rod have any effect on the metal ball if we brought it close to the metal ball if the metal ball had no charge? And we're going to look at that answer in a few seconds, and the answer might not be sort of what you expect. You may think that because the metal ball has no net charge, that the charged plastic rod, which has this net negative charge, won't have any effect on it, right? But in fact, we're going to see that it does have some effect on it, and we're going to see why in a moment here. But before we do, we're going to talk about charging by induction. Okay, so we're gonna basically take all the tools that we had in this previous setup here. We're going to take our metal ball and our charged rod, and in this case we're replacing the nylon thread that we hung things from by this this insulating stand that we have here. And so we start off with a metal ball with no net charge on it, just sitting on this insulating stand on the ground. Okay. We then bring this negatively charged rod close to our metal ball, and because our metal ball has some free electrons in it, we can have things move around inside the metal ball, right? So what kind of ends up happening is some of these free electrons will migrate to the right hand side of the ball, and we're going to end up with some net positive charge on the left-hand side of the ball, because what's happening, the rod is coming closer, it's repelling these negative charges. They're moving away as best they can while still staying in the metal ball. So we end up with a net negative charge on this side and a net positive charge on this side, right? And so what if at this point we were to connect a wire to this ball and then ground the wire? The wire would then connect to the ground. Well, these negative charges would whiz down the wire and end up in the ground, right? And if we then disconnected this wire, well, we would have robbed some of the negative charge that was in the ball already from that ball and put it to ground. And so what do we end up with? Well, we end up with a ball with a net positive charge now. Our metal ball has a net positive charge. The ground has the negative charge that we drove off the ball using our rod here, and we end up with this setup that we have here, right? So this is a way that we're charging by induction, right? So we're inducing this net positive charge on the left-hand side of the ball here, and by bleeding off this negative charge, we've charged by induction, we've charged our ball with a net positive charge. Okay, and so that's sort of the idea, and we're going to look at all these ideas much more in a much more quantitative way as we move through the next few sections here. But these are the sort of ideas that we're sort of just introducing in the video here, very qualitatively, right? And so if we look back at image B here, we can kind of already see what's going to happen if we're asking the question, how does this negatively charged rod interact with an electrically neutral, or at least a ball that has no net charge, like this metal ball here has no net charge so it's net electrically neutral. But we can kind of see what happens as we bring that negatively charged rod up to it, right? We drive away these negative charges, and these positive charges are in a sense drawn towards us, right? And so what's kind of going to happen? Well, if we didn't attach this wire and we just looked at the forces at play here, what would we feel? Well, these negative charges are farther away than these positive charges, right? So you're going to have some net attractive force between the positive charges on the left-hand side of this metal ball and the negative charges in our charged rod. There will still be some repulsive force from the rod and the negative charges on this side, but they're farther apart, and we're going to find that these electric forces are dependent on the distance over which they're acting, right? And so because we have the positive charges closer, we're going to end up with a net attractive force in this case. So if we go back up to this setup that we have over here, and if instead this ball had no charge on it, well, we would end up, maybe I'll draw it down here. Let me get rid of this for now. Have I left a spot here? Yeah, I have. Okay, so we can see that if we end up, and I'm going to try and draw this as best as I can. So this is our rod. It has a bunch of negative charge on it. As we bring it close, we end up getting positive charge and negative charge sort of splitting up over here like this. And so we will end up seeing a net attractive force between our rod and our ball because of this induced positive charge that we have building up on the side closest to the rod in the ball, right? And so that's sort of the answer to would a charged rod have any effect on an electrically neutral ball if it was just hanging here. So again, this is like our nylon thread sort of hanging the ball here, so it's free to move, right? So we would see these two things being drawn closer together, right? Okay, so there's also a nice sort of test your understanding at the end of section 21.2. And so what are we looking at here? We're looking at two lightweight metal spheres, each hanging from an insulating nylon thread. So maybe I'll draw those here. We have one, and we have a second one here. Initially, one of the spheres has a net negative charge, so let's make this thing negative. And the other one has no net charge. Okay, so this one has no net charge over here. If the spheres are close together but not touching, what do we expect to see happen? And so the textbook gives you guys some options if you read through there, but we'll sort of just talk through it here. So if they're kind of hanging here and they're free to do whatever we sort of want them to, well, what ends up happening? Well, we would expect that the same thing that we saw above would happen, right? Initially, we would start seeing a buildup of positive charge on the right side of our neutral sphere and negative charge on the left-hand side because of induction, right? The negatively charged sphere is going to induce charge in this electrically neutral sphere. So when this happens, what do we end up seeing? Well, we're going to have a net attractive force, right? So some short time later, we're going to end up with the two of these things touching, right? And so when they finally do touch, what's going to end up happening? Well, both of these are made of conducting materials, right? They're both metal balls, so some of this negative charge is going to actually move over to the electrically neutral left-hand sphere, right? And so we're going to end up with a situation like this, where we have negative and negative, right? Well, now we have two sets of like charges, and they're close together. So we're going to end up with a net repulsive force. And again, in this situation, we're talking purely qualitatively here, right? Like there are no numbers. We're not doing any calculations, so we're just kind of getting a sense for it. Later on, we're going to do things like this, where we actually do calculate the magnitude of these forces and how all this stuff happens, right? So let's say this is A, this is B, this is C, and then in D, what's going to happen? Well, this net repulsive force is going to end up giving us one ball over here, negatively charged, and another one over here. And at this point, we're going to reach some sort of equilibrium. These things aren't going to move anymore. They have a net repulsive force here, but because they're tied down, we have whatever, some force of tension here. We have some force of gravity here, and we have a net repulsive force keeping us apart, right? And so it reaches some sort of equilibrium, and these things sit some distance apart until something else would happen, right? So that kind of answers that question. Okay, so this basically brings us to the end of this video. In the next video, we're going to look at Coulomb's law, and we're going to start doing some calculations. And as I mentioned, we're going to try to have something like one video per section, but we're going to be covering one chapter in the book roughly per week. So these lecture videos don't map to a full lecture, right? Like this video is going to end up being something like 45, 47 minutes or so. And so we're going to want to cover a full chapter each week roughly, which is going to map to about, well, it'll depend on the chapter, but there's going to be some number of videos in there. They're not going to map directly to lectures, right? So you can watch these at your own pace whenever you want. But you're going to have to get through the full sort of set of videos before you do the assignment for the section, right? And the assignments are what's going to sort of dictate the pace, right? I'll talk, or I will have already talked more about that in the introductory material for the course. But yeah, just keep that in mind. These aren't sort of intended to map one-to-one to lectures, and so they're sort of shorter. So you'll watch a few of them whenever you want, and sort of get to the end of the material in that chapter at your own pace. Okay, so I'll see you guys in the next one for Coulomb's law.